we will talk today about the important concept of process capability. So the learning objectives today are to describe what is meant by process capability, to calculate process capability using the indices CP and CPK, and to discuss the uses and the drawbacks of these indices. We began the course by discussing what product quality means, and we discussed Dr. Duran's definition for quality as fitness for use. And we extended this to consider meeting or exceeding customer expectations. And we came to the conclusion that quality is relative and offers value to our customers. We mentioned then there were different dimensions of quality, and we were reinforcing the idea that quality has many different aspects and cannot be defined easily by one single phrase or simple idea. Quality may have different meanings for different people, for different products, and even for the same products, it depends on the target market. It depends on the different requirements of the different users. For a complete definition of product quality, we stress the importance of identifying the needs and the expectations of the customer. We talked about how product designers take these needs and expectations into account, and then they select features of the product to create a design. The target and limits of variation for these features are then selected so that the product can be produced at a reasonable cost while meeting the customer's needs. So these product features, which must be measurable, are called then the quality characteristics. And the targets and tolerances together the designer has come up with are called the specifications, or the specs for these characteristics. And this is what we're going back to now. We're going back to the idea of product specifications in order to talk about the capability of a process. So, if a process is normally distributed, the condition of the process can be fully described by its mean and its standard deviation. And if we have a sample, we can calculate the process mean, or we can estimate the process mean using the sample average X bar, and the process standard deviation can be estimated using the sample standard deviation S, as we've done before. Now, if we have a normally distributed variable, so our variable here X, and we take a sample, so here is an example. The random variable that we're interested in can take very different values. It can be small values going up to larger values. Now we take our sample, we take all these values, and we calculate then our sample average and our sample standard deviation. And with these we can get our model of our population, which will be, of course, centered around the mean estimated by X bar and have a standard deviation estimated by the sample standard deviation. So taking our model then, as we said earlier, the product specifications are the targets and limits of variation for the particular product features so that the product can be produced at a reasonable cost while meeting the customer needs. Now, using the model of population for our random variable, we can then compare this distribution to the product specifications. And for one single normally distributed variable, we can consider a upper specification limit, or USL, and a lower specification limit, or LSL. And the process target then would be centered the midpoint between the upper and lower spec limits as shown here. And what we have here, of course, is the mean of our actual variable is centered according to the target. So a process that produces all of its units within the upper and lower specification is said to be capable. To assess its capability, the process, represented by our distribution here, is compared with the specifications it's supposed to meet. And if all of the process is not within the specification, you need to make adjustments to the process in order to bring the process to its full capability. And this analysis is called then a process capability analysis. So for example, if we look at this qualitatively, when a process is compared to a given set of specifications, so compared to the upper spec limit and the lower spec limit, there are several possible situations that can happen. For example, the process could be well-centered and could have very low variability compared to its specifications. So if I draw this here, the process could be well-centered and have low variability according to its specifications. On the other hand, we could have the fact that our process is off-center, and even though it may have low variability, part of the distribution actually extends beyond either the upper or the lower spec limit. And these ones, this part then would be out of spec. We can also then have the situation that the process has too high variability. So even though our process is centered, the variability is too high, and we have values of our random variable that extend beyond the specification limits. And finally, we can have even the case then we have both. We have a process which is not only off target, but is also widely distributed. This is not a very good picture. So you have on both sides values that are outside of the spec, but more on one side than the other. So these drawings here, these are qualitative assessments of whether you have a capable or incapable process. And in these examples, you can see whether it's the process variability or it's the process centering that is causing the problem in the process. But often we don't have these pictures available to us. We need a quantitative assessment of the extent to which a process meets its specifications. For example, we may want to compare the capabilities of two machines, on what they produce, or of two vendors, what kind of product they're giving us, or we may want to start to monitor our process and monitor the progress to reach a certain capability while making improvements. So for these, we would find a quantitative value much more useful than pictures. So here we can make use of capability indices, which provide numerical measures quantifying the capability of a process. And the two most common process capability indices are CP and CPK, which we will define now. But first, I want to go back quickly to the normal distribution, just to remind us of its characteristics. So we discussed in Module 2, when we have a normally distributed variable, it is centered around a mean, and there are 2 points of inflection located at a sigma distance, standard deviation from the mean. So we have now what we did with an example, I think we used the example of tabletops, is that we were saying that if our tabletop length is normally distributed, then we can be sure that about 68.27% of our tabletops will fall within plus or minus 1 sigma, 1 standard deviation of the mean. We also said that if we look further out at plus or minus 2 standard deviations from the mean, that about 95% of all our tabletop lengths will fall within 2 standard deviations of the mean. Finally, if I extend my picture a little bit here, if we look at the distribution and we go out to 3, plus or minus 3 standard deviations for the mean, in this entire area, I'm going to shade this in now. This entire area up into plus or minus 3 standard deviations of the mean, we have 99.73%. Oops. Oh. 99.73% of all the data is within plus or minus 3 standard deviations from the mean. So, this means that if a random variable is normally distributed, then almost all the data, 99.73% of the values, will be within 3 standard deviations of the mean, which is a total spread here of 6 sigma. And it's this 6 sigma that we will use now to express the process overall natural variability.